I'll be presenting on behavioral modeling with machine learning, or more like the challenges that we've had with modeling customer behavior with machine learning. So I'm the director for data ops and data science at IGT iLottery. So what we do is we operate lottery services for multiple state governments in the US, Europe, Asia, all over the world. And so lotteries, you might imagine as tickets that you get in the shops, but that's not the only form of lottery. Lotteries is also played online. There's also games. So it's not lottery is not just about the one ticket that you get and you might win millions of dollars, but it's also small games. So that's what we offer, and in that we are trying to improve the customer engagement. How can we improve the enjoyment that a customer can get from playing games? How can we bundle our products, and what is it that people are what is it that motivates people to play a lottery and other things. So in that, we are trying to understand how we can apply data science and machine learning to understand what people are actually looking for. Now, I'll start with an exercise. So, room full of very smart people. I guess if I ask a question, you've already calculated 2 plus 2 is 4. Um, so now, how about this one, which is slightly more complex? But yeah, very smart people. Probably some of you have already have an answer in your mind. So what this I wanted to just demonstrate is that how our brains work. So we have something called as System 1 and System 2. So Daniel Kahneman, who won the Nobel Prize in behavioral economics, so classified the way we think and way we make decisions into as brain operates as System 1 and System 2. System 1 is the one that is fast, subconscious. So when you saw the 2 plus 2, that is when your System 1 activated, and it in a very quick decision. It was something that was you could have done it subconsciously, very automatic. You easy to make your everyday decisions. Whereas System 2, it's a bit slow. It's more conscious. You need to make a bit more effort. So when you wanted to evaluate the second equation, 17 by 24, you had to make a little bit of effort. So you needed to engage your System 2. That's when you use to make complex decisions, but it is more reliable. To think of this, psychologist Jonathan Haidt has the analogy of rider and the elephant. So here, elephant is the System 1. Uh, it's quick. It's your brain that has evolved over to survive, and the rider is the one that is the more cognitive, the calculating um, part of your brain. Now, the rider thinks that it's the one that is riding the elephant, but or making or directing the elephant, but it's actually the elephant which is driving most of our decision making and the way we think. Now, so to there are a lot of behavioral traits that influence how we make decisions. Some of them that are listed over here are like reactance. Reactance, which means we just do something sometimes because it's not someone asked not to do. Possibility effect is when we disproportionately value the possibility of winning something. Anchoring effect, when quite often this is used in negotiations and something like a salary negotiation, where you anchor to a point and then your choices are the answers are based due to the anchor. Subconscious nudges and priming. So sometimes marketing will have subconscious nudges for you to direct you to buy a specific product. Loss aversion, we are more prone to avoid losses rather than an equivalent profit. Hedonic treadmill, so we have a level of happiness. We get very happy, and then that becomes our standard, and then again we need some other additional stimulus to be happy, or if we get too sad after some time, we come back to our stable level of happiness. Right turning retail, so quite often in shops, uh, the shops will, most people turn right first, and that's why a lot in many shops that you will visit, you will see that a lot of the product placement is on the right. Um, how can we use this in decision making? So we have data scientists and economists. Now, economists believe that people are rational. Traditional economics and traditional data science will understand that people have a rational. They can understand data, and they can they make decisions with all the information that they have. But in reality, people are quite irrational. Sometimes it's very difficult to understand the decisions that uh, someone will make. And that's what, so data that will give you what is happening historically, but it's not informing us why is it happening. So that's what to understand behavior and why people make certain decisions. It's very important to understand psychology and what could be the reasons behind people making decisions. So some of the behaviors that we discussed, I'll just give a more explanation of what we are looking into. So reactance. So we often do things just because someone tells us not to do. In many cases, is something like motivation for gambling, or someone in our lives has told us not to gamble. So that piques the interest. Okay, why should I do that? And a good example of that is in vaping, for example. Vaping is something that is not advised, but you might see that a lot of teenagers are nowadays having vaping. It's quite a prevalent problem. So sometimes we want to do just because someone has said not to do. I think if we start having old people or middle-aged people starting vaping, probably it'll be less attractive. Possibility effect. So this is when we highly we are more drawn to some unlikely events. To give you an example, in this Dishum restaurant in London, if you've been to, for their regular customers, they have something called as a keyring. So if you give them a keyring between on weekdays before 6 p.m., if you go, they give you a keyring and they'll give you a die, six-sided die, and if you roll a die and the die you score six, then your bill is free, so you don't have to pay. So it's now, as an economist, that is a 16.66% discount, one six the probability, and so that's about 16.66% discount. But for a human mind, getting a meal for free by the roll of dice is a completely different thing. It's not the 16.6% discount, and that's what it excites a lot of people to take that as a chance. Um, Anchoring effect. So that's when we see one number and then our immediately we start making decisions based on the number that we have anchored against. So as an example, school children were given the first equation, 8, 7, 6, 5 by 4. And other set of students were given the same equation, but the other way around. And because the first equation started with a higher number, that batch came up with an estimated figure which was much higher up at, I think, 2000 something, whereas the second batch, where the numbers were from 1 to 8, that came up with an answer which was significantly um, lower. I think it was in the 700s or something. So studies showed that in time constraints, there was obviously a time constraint which was mentioned for the students. People will extrapolate the number based on the anchor that they've seen. So when you start with 8, you immediately start thinking that it's going to be a higher number. Whereas if you start with a smaller number, our brains start thinking about a lower answer. And this is subconscious nudges. So if you've ever been to Schiphol Airport or some of the airports, so what they did was the toilet cleaners, they had a very uh, uh, challenge with cleaning male toilets, spending a lot of time because there was a lot of people were not pointing correctly. And so what they did is someone suggested that, hey, let's put a fly in the toilet on the in the men's urinal. I don't know if you have seen such urinals. They are quite in many other places, although in this one is from Schiphol Airport. And so what it did is it reduced the spillage on the floor, and it reduced the effort or the time needed by the toilet cleaners to actually clean. So just putting an image of a fly in the urinal actually reduced the effort and time needed to clean the toilets. So this is like a subconscious nudge, and actually marketing uses some of these quite a lot. An example of this is decoy selling. I don't think I'll be able to play that video and the audio, but I'll give you an example of what this was. So, The Economist had subscriptions, and oops, I don't think you'll hear the audio, so I'll just let you know what is the effect. When Economist had created three choices, one was the Economist subscription for only print and web subscription, an only print subscription, and an economist.com subscription. Now, people found it sort of confusing to compare multiple choices. So it was interesting that when they put a decoy uh, print only, it doesn't make any sense. There's a print only subscription, and there's a print and web subscription for $125 and $125, and there is an economist.com subscription only, which is web only, which is $60. So when just by adding this subscription as an option, the best subscription or the best choice for 84% of people was the print and web subscription, which was $125. In absence of this print subscription, the best choice or the most likely choice that people chose was the economic.com subscription or the web subscription. So just by having as an option, which was didn't have any value in itself, but it increased the probability that people buying a print and a web subscription, because people could compare. Okay, I'm not comparing my a digital only or a print only, but I'm going to get a bundle. So that's how we can design choice architecture based on the behaviors that we have. Loss aversion. So many of you must have already heard of loss aversion, and it's actually not a bias. I mean, it is bias, but it's not a bias. We have evolved to avoid losses. So, as an example, if four people start with $100, 100 pounds each, and tossing a coin, heads wins 50%, tails lose 40%. As we know, 50%, flipping a coil over a point of time, I'm always going to make a profit, because I'm going to throw half heads, and I'm going to make a 10% profit on that. So let's see what happens if four people start. So there's two people throw heads, and they get 150, whereas two people throw tails, they get 60 and 60 with a loss of 40%. So starting with $100 each, which means investing $400 each overall, the total money pot is now $420. So overall, there's a increase in the value. Now, if we throw the coins again, is the first guy is two heads. He's at 225 second, and the third guy's head and tail at 90 pounds, and the fourth person, due to two tails, is 36 at 36 pounds. Now, although an economist or a mathematician would say, no, you need to continue, keep throwing by throwing a coin, because as probability says, you're going to start making profits. But as a human mind, the person who's had two tails is going to exit the game, because the loss seems quite a lot, and that's what, yeah, our brains will avoid losses and try to not engage in a game. So this is when we are trying to reduce what our minds are trying to do is reduce variance. I mean, bias variance trade-off in machine learning. It's also there in our brains. We are not we don't significantly what are called biases are more like human brains are trying to reduce the variance. We want a bit more consistency that we can expect. Now, hedonic treadmill, so where we go, something makes us happy and then we stick there. We stay in that happy mode, but at some point, then that becomes our expected level of happiness, and then we come back to our stable happiness level. So, good things happen, bad things happen, but we have a stable level of happiness. And so, as you've seen, there's a lot of more behavioral traits, and they can be quite confounding. Is there a way to model these? So there are some models, not machine learning models, but models proposed that could to understand how human behavior can be modeled. So one of them is Kano model. So this was proposed by Dr. Noriaki Kano, who is a professor at the Tokyo University, who mentions features that are in your product. How much are they valued by customers versus how much some of the features which are not valued, and how some features which are delighters in the at the beginning might become a basic need. A great example is your mobile phones that unlock just by face, and if now earlier it was delighter, now it's become a basic need. A good example of features. I mean, Kindle. Most of us, when we had started with Kindle, we thought we're never going to have books, but books actually have another purpose as well. So books have a purpose of being a gift. You can stock your shelves behind your walls with books. You can't do that with Kindle. So there was a value or a feature of books which was not evident, but Kindle, having Kindle, we realized that okay, we actually do need books, and books have actually we sell more books nowadays than we used to do before Kindle. Another model is the scarf model. So what by David Rock. So what he says is that humans are always evaluating everything as a reward or threat. So anything that we see, our brains are always trying to understand: hey, is it something good for me or is it something bad for us? And the scarf model, which means we are trying to understand, maintain status, certainty, autonomy, relatedness, and fairness. So there is this capuchin monkey fairness experiment. It's a very famous experiment. I think many of you might have seen it. There's two monkeys. One monkey gets um, um, a cucumber, and the other monkey gets a grape for the same work. Initially, both of them are happy to do their job, and when the other monkey, well, sorry, one monkey sees the other one getting grape rather than cucumber, it starts getting understand that it's not fair, and they want something else that someone else has. Okay, so modeling behavior is very hard because every person is unique and with a variety of interests. We want to help people what they want, even when they are not sure exactly what they want. So when people are logging into lottery portal, they're trying to play game or just for entertainment. We're not sure, or they are not sure what exactly they want, and we want to see how we can give them the suggestions that they want. Things are non-stationary, very context dependent, mood dependent. The games or the things that you would watch in the morning versus what during the day, or versus in the evening, or when you're on a weekday or a weekend, would be completely different. We have a large data sets, but very small data per player. There's cold start problems everywhere. So new players being added, new games being added, and more than just accuracy, we also need to ensure that we have offer diversity, new games, freshness, and fairness, avoiding feedback loops that the recommendations that we offer. And then person uses those recommendations, and then we just make those. So modeling behavior is quite hard, and just not in our business, but in many cases. One of the biggest challenges for autonomous driving is going to be understanding human behavior and the way humans will react when we have autonomous cars driving on the roads. So MIT researchers have been trying to solve this problem, and they are coming up with a relatively simpler solution to see how they can model human behavior. So they try to break this multi-agent problem into smaller pieces to tackle each one individually. So what the method, they are calling it as M2Y. So what they're doing is they're taking a complex set of decisions that need to be made by the car to into smaller, like yielding to a jaywalker, yielding to other vehicles, yielding with direction failure, merging into crowded traffic, and other things. And how do they how what the overall model it does is it has an influencer model that does a marginal prediction, and then that marginal prediction goes into the conditional predictor, which is the reactor, and then that gives an n by n joint samples, and then a sample is selected that gives you samples of what would be the possible outcomes based on the conditions that have happened. So breaking a bigger problem into smaller problems and having the conditional probabilities of what a person would do in case of the other situation happening. So that is one way that we are trying to see how we can model customer behavior by breaking it into smaller um, problems. So one of our like any business, one of our goals is how to optimize customer lifetime value. So how to engage players better, how to keep them for longer, and how to give them the best suggestions. So breaking that problem into player engagement, how can we engage our players by giving them the best or the most likely suggestions that would make them happy. How to predict and departure, how to see customer might be churning or might be disengaged, and how can we try to drive that engagement. Personalization, so creating personas and then segments that would help us to deliver the right content to the right players, and also identifying anomalies and any fraud or any problematic behavior. So some of the behaviors would be if we model, we might be able to engage our players for longer and also increase the customer lifetime value. It's not going through all, but we might be able to take a look at some of the problems. So um, the game players, there was not us, but I think there's a very famous game called World of Warcraft, and so they tried to analyze the personalities of some of the players who play. And so they identified, they classified players into achievers, explorers, socializers, killers. So achievers were playing just to earn points. It's just like something on a Stack Overflow. Some people are very helpful, want to help, and there's explorers who prefer to know the entire, prefer to explore the various parts of the game. Socializers want to play with different players, and killers, they just want to yeah. Quite aggressively play in the game. They also try to identify which players can play with, because it's multiplayer game, which players can play along with each other. And they had a very relatively simpler heuristic based decision tree to identify or classify the players into various personas. One of the things that we are working on is obviously building a great recommendation engine. So we have landing pages for games, and we want to ensure that we are able to, for every player, we're able to offer a great recommendation of the games that they would be able to play, something like Netflix or YouTube. So a very popular or the workhorse of recommendation engines is the collaborating filtering. So you must have, so you have on x-axis the various games that we have, and on y-axis the number of all the players that are playing. So it captures the interaction of a player playing a game and the number of times that they've played and the number of games that we have. So that gives you the interaction matrix. It will be a very sparse matrix. So and then you create two dense matrices of from that to for the users and the items, and then you model that to identify. what is the this matrix factorization matrix that you can identify for uh, collaborative filtering. Now there are other, I think, content-based models. The collaborative filtering model is based only on the interactions that you would have, but it will miss on the similarity between games. So if there's multiple games which are similar out the characteristics, so you might miss out on that. So content-based models would be working on if a player has played game one, game two, then and game three is similar to game one, then I just recommend game three. So this is more like a model for every single player, and so this captures more of the interrelationship between games, how similar they are, how different they are, but would miss out on the interaction, which is the gameplay behavior that we see from other players. And so then there are hybrid models. So hybrid models use latent vectors and the item later vectors. So that will be, instead of having a specific per player, you would have the characteristics of players, and you would use them and the characteristics of the game to model that, and that would give you a slightly denser matrix. And again, you do the same, which is matrix factorization. And because this is Python, and what we had been using was one of the matrix factorization techniques called Light FM, which does the hybrid modeling. Now, so this was the traditional way in which we had been developing the recommendation engine, but we need to evolve that, because game now we have much more richer information with which we are able to understand customers a bit more better. So how we're trying to evolve this is we now have contextual event data. So the impressions, the games that a player has played, the interactions that he's had, like them, the amount of time that they have played, the amount of the various teams that they've played, other things, and then contextual data, which is the devices that they've used, the time and date, or rather the time of the day or the day of the week that they've played, the location. So games might be different for different locations, and then also the game data, so features of the games, and profile settings based on the profile settings that the user has set. So all these information we want to use into our recommendation engine, and so we are evolving into how can we use contextual bandits into the modeling of our recommendation engine. Some of the things that we need to control for is causality. So correlation will not be causality. Just because there is a lot of people are playing a specific game doesn't mean that the game is really nice. There could be some reasons. This is an example from spurious correlations. So what you see is a very highly correlated data between people who drowned after falling out of fishing boat versus marriage rate in Kentucky. Now, I think it's this data which has shows high correlation actually has no relation to each other. Although I'm married, and some people or might agree that people drowning and marriage rate might be actually have some reason for correlation. Um, and then we also need to control for feedback loops. So feedback loops is if we because we've made a recommendation, the player has played the game, and that becomes the data that goes into our model, into our training data for our model. Again, we make the same recommendation, so it becomes into a closed loop. It's something like on YouTube, you watch a specific genre and video, and then you keep getting recommendations of the same genre, and sometimes so we need to add some freshness to that. Open loop is when if the user is able to search games and search the games by uh, specific category or something, or we are trying to add how can we add some randomness into the recommendations that we make. So there's quite a lot of things that we need to improve into our recommendation engine so that we can understand the customer's behavior and understand how we can model that. Um, and I'm coming towards the end of my slides. So we are trying to see how we can offer, make lottery games offer happiness with our games, and how we can engage players better by giving them a smaller happiness, and it's being interested in the big things while being happy with the small things in life.